Hi, welcome to the first lesson in Educator Statistics course. Today we're going to talk about descriptive statistics versus inferential statistics. So here's the roadmap for today. First, we sort of need to distinguish how statistics is different from other mathematics. Then we're going to talk about how descriptive and inferential statistics separate. Finally, we're going to talk about populations versus samples. And then we're going to put all of those ideas together and look at how population, samples, descriptive, and inferential statistics all fit together. So first things first, how is statistics different from other specializations in mathematics, such as trigonometry, geometry, calculus, linear algebra, right? Well, statistics is different because it's the science of classifying, organizing, and interpreting, or what we call analyzing, data. And you might be thinking to yourself, hey, science? I thought this was mathematics, right? Well, actually, statistics applies much more to science, and because of that, it's so important in mathematics. And let me explain that link to you in just 1 second. First, I want to step back and think about high school science for a moment. A lot of high school science is concerned with measurement. We're going around measuring things and measuring how fast people run and how fast things are dropped and how much things grow and how much things weigh and how big things are. And we're really gathering a lot of data on measurement. Then we find patterns within those measurements. And that's really basically the fundamentals behind high school science. And those patterns can often be described as mathematical formulas. Now, I don't know if you have this experience, but some of you may have had this experience of trying to derive the gravitational constant. So to some of you, this equation might look sort of familiar. D equals 1/2 gt squared. So D stands for distance, G stands for the gravitational constant, and T stands for time. And so some of you may have had the experience of dropping things off a building and timing them and putting in these numbers to try and figure out what G is. Now, G, theoretically, is supposed to be 9.8 meters over square seconds. But very, very rarely do you calculate exactly 9.8 when you put in distance and time into this equation. So often science students think, oh, I'm terrible at science, I'm not getting the right answer. But actually it's because all of these measurements are inherently a little bit sloppy. Now granted, high school students might be sloppier scientists than other scientists, but in actuality, all science experiments have measurement error, and there's variance that comes with measurement. There's always a little bit of jiggle in that data, and often we don't pinpoint the exact right data. Even when you look at something like measuring someone's height, you might have 10 people measure the same person's height and come up with slightly different answers. And it's not because they're trying to cheat, but that person might take a deep breath, or slouch a little bit, or maybe they read the tape measure at their hairline instead of at their actual height, right? So there's all these different reasons for measurement error, and all science is actually fraught with measurement error. Well, because all experiments, even the really good ones at CERN and MIT and Caltech, all experiments will have a little bit of sloppiness. And that's because we're dealing with measuring the physical world. It's not that we're looking at terrible scientists or just real messy. It's just that inherently in measuring the world, we're going to have a little bit of sloppiness. Now, because of that sloppiness, even the best experiment will produce a scatter of numbers. So even best experiment, as well as, the worst experiments, they'll produce a scatter of values or measurements. So that's sort of problematic, right? You don't get just one number like nice 9.8 gravitational constant. You instead get this scatter of numbers. So how do we deal with that scatter? Well, that's where statistics comes in, because statistics is really the math of distributions. Now you could see how the math part and the science part sort of go together. Statistics was really invented because we really wanted to do better and better science. So we even have a special name for the scatter of measurements, and that's called a distribution. Not only that, but we're going to look and see how we can go from frequencies of these values in order to get probability distributions of these values. Those are also going to be called distributions, probability distributions. Now, one thing that should come to your mind is that when you have a scatter of values or a whole bunch of different probabilities predicting different values, then you're not going to have just one number, you're going to have a whole set of numbers, right? And so because of that, we're going to have to deal with the mathematics a little bit differently. We're not just computing one number at a time and looking at one number and adding things to it, subtracting things to it, doing things to it. Instead, we're looking at entire distributions. How do we treat these distributions? How do we interpret them? That's the question behind statistics. So you might think, working with whole distributions, that sounds sort of problematic. And sometimes it might seem like it. It might seem like, wow, these equations are pretty complicated because we have to deal with the whole distribution. But also, you get some great stuff out of working with distributions. One reason is because distributions are often much more predictable than individual values. So distributions, more predictable than individual values. And so models of distributions, or theories of distributions, can often predict the mathematical nature of randomness. Isn't that great? They're predicting randomness, right? And so that's what statistics is a little bit about. It's dealing with that randomness and taming it. All right, so how is statistics different from other specializations in mathematics? Well, it is born out of the science of classifying, organizing, and interpreting data, or distributions of data, to be more precise. And because of that, statistics is the mathematics of distributions. Statistics is actually fundamental in all sciences, in both natural and social sciences. I'm a social science professor, a psychology professor by trade, but even in the natural sciences, all these discoveries that you've heard of, they've only come about really through rigorous applications of statistics. In physics, biology, economics, psychology, you name it, statistics has left its mark there. There's really two skills that you need to know once you enter into statistics. The first is the skill of data description, or what you can think of as exploration. Often you could think of it as just an open-ended examination of the data. Let's look and see what's there. We're looking for patterns, and often it's helpful to make a graph or to look at averages and standard deviations, what are called summary values. When you're looking for patterns. These are tools that help us see patterns better. But the problem with just exploring or describing data is that you're not actually able to come to any conclusions. You have to sort of rein yourself from making conclusions when you're just doing descriptive statistics. That's where inferential statistics will come in. When you make inferences in statistics, now you're doing a much more strict examination of the data according to set rules. Then you judge whether these patterns that you find through description are likely or not, according to theories and different models that you may have set up. And at the end of inferential statistics, you should be able to make measured conclusions. Often in science, we don't say statistics has proven this theory or completely disproven this theory. Instead, we make much more measured and qualified conclusions. All right. So those skills of description and inference apply directly to descriptive statistics and inferential statistics. The thing that's different now is you want to think about those skills and how they apply to distributions, right? And so here's how descriptive statistics applies to distributions. These are the concepts and tools that you need in order to analyze sample distributions. Used to describe or explore sample distributions. So we've just taken those same concepts of what describing data means and we've applied it to sample distributions, distributions that we've plucked out, a set of data that we've plucked out. In inferential statistics, what we need to do is then apply inference to distributions. So here, it's the concepts and tools to reason from a sample distribution to make some inference, to reason from a sample distribution to a larger, what we call population distribution. So in inferential statistics, what we're doing is using those skills of inference to go from sample distributions, but not only just to understand the sample, but to make some inferences about a greater, larger population, to sort of go beyond our actual data. In descriptive statistics, we just stay with our sample. We don't make any inferences beyond what we have. All right, so it behooves us to sort of figure out, okay, then what's the difference between the population and the sample distribution? Well, here, it might be helpful to just think of the population as sort of like the truth. This is what we're really interested in, right? So is it the truth? This is the truth. So this is the thing that we really want to get at. If you think about the gravitational constant, this is that magical value that's really out there in the world. But the sample is not actually the truth. It's just like a little bit of that truth, right? So when we drop our objects from the top of a building and measure how fast they come down, right? We're really getting samples. And from those samples, we're trying to get at the truth. The sample is not the whole truth, but the sample does provide a window to the truth. But it's important to realize that the sample is not the actual truth itself. This is not what we want to really, really know about. We really want to know about the population, but we're using the sample in order to know about the population. All right, so some pros and cons, right? So some pros of the population is this. Because it is the truth, if you happen to have all the information about the real population, it will be absolutely 100% accurate. However, here's the con. It's almost impossible to get. It's almost impossible to actually get the truth, the real population truth. For instance, let's say you just want to know what the real average height of every person in the United States is. Well, in order to do that, you would have to get measurements from every single person in the United States. And all those measurements would have to be 100% accurate. But let's say I give that to you. You even do that. By the time you finish recording all of those measurements, some people will have died and new people will have been born, right? So all of a sudden, your measurements wouldn't be accurate anymore, right? So it's almost impossible to actually get the entire population. Often in statistics books, they'll pick a small population. Like they'll say, consider all the people who attend your school. and they'll just shrink down the population so that you could actually think about it without sort of feeling like your mind is being blown. But in the real world, it's basically impossible to get the real truth. On the other hand, the sample has the pro of being convenient. It's actually really easy to get data from just a sample of the population, right? You don't have to get the whole population, you just have to get a sample of it. And so it's really convenient and easy to get. But here's the big con that you need to worry about. The con is that the sample might be what's called biased. And by biased, I don't necessarily mean like the sample's like racist or prejudiced in some way. I just mean that the sample may not be representative of the population. The problem with that is this. When we look at our sample, we're going to use our sample to try to get at the truth. If our sample is really different from the truth, then it might lead us astray, and that's called being biased. All right. So when we describe the population in terms of numbers and we get some summary values for the population, those descriptive values are going to be called parameters. And a friend of mine who teaches statistics would say, population, parameter. Okay. On the other hand, for samples, you would use what's called statistics. Now, this word for statistics is the same word as the word for the class. But statistics covers all of statistics, descriptive, inferential, population, sample, all that stuff. This is a sort of smaller use of that word. So, population and parameter, samples, statistics. Ta-da! All right, now let's put all those ideas together. So, how do we put together descriptive and inferential statistics with populations and samples? Well, it helps to sort of ground ourselves by starting off with the idea that what we're really interested in knowing about, is the entire population. We really want to know about the real population. And let's deal with one population at a time for now. But often we don't have the population's entire data in front of us. We only have a sample of that data, right? So this is our wish to go from sample to the population. But remember, the sample can be biased. That's problematic. So here's where statistics comes in. From samples, we compute statistics. And from populations, we could know the parameters. But we often don't have this link either because we don't know anything about the actual population. So here's where we are. What inferential statistics will help us do is make this link. How do we go from statistics of the sample to population parameters? This jump, this inferential jump, is going to be made through inferential statistics. However, in order to go from the sample to its statistics, we'll use descriptive statistics. And this is how it all fits together.